So let's welcome LaSalle Academy, Team 6617. Take your seats. So the first question is the easiest one. Would you tell us, please, what your name is and what year you are? And then I will turn you over to the judges.
My name is Audrey Cryan, and I'm a senior.
My name is Joshua Reno, and I'm a senior.
I'm Allison Paul. I'm also a senior.
I'm Eric Salisbury, and I'm also a senior.
And I'm Eileen Fu, and I'm also a senior. Judge panel, I'm Karen Bliss from Virginia Military Institute. This is Dan Connors from IBM and Ben Galuso from Shippensburg University. You will have 15 minutes for your presentation. I'll let you know when you have 2 minutes left. I'll give you a signal. And then following your presentation, we'll have about 5 minutes of questions, and then we'll be done. So you may begin.
Car sharing has become a popular mode of transportation. However, because it is relatively new, questions have arisen as to its cost efficiency and its staying power in our transportation world. We divided the population into groups of low, medium, and high with respect to time driven and distance driven in a day. Then, we created a model to rank 4 cities: Poughkeepsie, New York, Richmond, Virginia, Knoxville, Tennessee, and Riverside, California, by how well certain car sharing models work in those cities. The models we were asked to compare were round-trip car sharing, one-way station, one-way floating, and partial ownership. Then we used our model from part 2 with the addition of self-driving and fuel-efficient cars to re-rank the cities. To simplify our model, we used certain assumptions. Our first assumption was that travel time and distance in a car is proportional to commute time. If a person lives close to where they work, they probably live close to other amenities, such as gas stations and grocery stores. If they live further away from where they work, they probably live further away from those amenities. We made people stay in the same category, so if they were assigned low time, low distance, they remained low time, low distance. We kept our analysis to the continental US, and we excluded dependents, such as children, because they were never traveling alone. We took data from the 2010 census of commute times per zip code in the entire continental US. When we graphed these times, the histogram was almost perfectly unimodal and symmetric, so we knew that we could use the normal model. Using the normal model, we assigned z-scores of -infinity to -1, -1 to 1, and 1 to infinity for the low, medium, and high groups with respect to commute time. Now Josh will continue to talk about commute distance.
So for our model, we wanted to look at the driving trends of US drivers. So Audrey talked about our time model, and I'm going to talk about our distance model. So we split up our distance model into urban distances and rural distances, as you can see on the slide, and that's important because they're going to have very different driving distances. As you can see, both histograms for urban and rural areas are unimodal and symmetric, and so therefore we can apply the normal model and to model the distribution. So the way we got these data points was we took a stratified random sample of all US zip codes for 30 sample zip codes, and we then took each of those zip codes and put them into an algorithm that allowed us to receive the distances based off street maps. So as Audrey talked about, we used z-score ranges of -infinity to -1, -1 to 1, and 1 to infinity. And this is important because we chose those distributions just based off how the normal model works. And as you can see on the slide, we showed how the z-score ranges translate in terms of miles and minutes into actual time ranges and distance ranges. So we took our time model and our distance model and put them together, as you can see, and we assigned low, medium, and high states based off those z-score ranges for both time and distance, and that gives us 9 combinations, as you can see. Now, each block represents one of the combinations, and since we took a random sample of the US, those data points should each be representative of the United States. And since they're representative, they should therefore, each of those blocks, the percentage of data points in each of those blocks should therefore represent the percentage of US drivers who carry those driving attributes. And that lets us make some very important generalizations about the trends that we see. So for example, people who drive long distances in medium amounts of time represent about 1/3. They represent that middle right block. And that's important because that's a very expected driving trend. People who are driving on the highway in the morning are going to be driving long distances in medium amounts of time. It's also important for us to note that those who drove long distances in short periods of time and short distances in long periods of time, the bottom right and top left blocks, those total represent about 1/30 of all US drivers. And that's, again, a very expected driving attribute because people are just not going to be driving those kinds of time to distance ratios. Now, overall, this is a table of the percentages for each of those categories. And it's important that we can note that as distance increases, commute time increases, and that's, again, a very generally expected trend for driving. And ultimately, our model allows us to take time and distance by looking at zip codes and classify each zip code as having a specific driving time, a specific commute distance, and that lets us make some very important predictions. Now, Allie will talk about car sharing.
So to model the future growth of each of the car sharing services in each of the 4 cities, we used a probabilistic model called Markov chains. So first, we divided the population into 3 categories: car sharers, car owners, and public transit users. And then we are going to look at the probability that a person in a certain state stays in the same state or changes states. So to model the probability that a non-car sharer joins a car sharing service, we used the sigmoid function, which is a great choice for a probability model because it is valued between 0 and 1. So you can see when x increases, the probability is very close to 1, and when x decreases, the probability is very close to 0. So x can be considered as the incentive for joining a car sharing service. So this incentive should decrease when the cost of the car sharing services increase, and it should increase when the car sharing services become more popular. So we write x in terms of both the popularity and the price in this equation, where S of t is the number of car shares at time t, and p is the price of the specific car sharing service, and this price is dependent on the characterization of like low, medium driving categories that we talked about earlier. K and C are constants that we chose, and we chose these constants so that the popularity and the price would have similar weights in the mind of the user. We then incorporated this model into our transition matrix for the non-car sharers to join the car sharing programs. And for the other elements of this matrix, we used reasonable assumptions because this data was difficult to find. So for example, we assumed that car sharers would be equally likely to stay as car sharers or invest in a vehicle or convert to being a public transit user because it was difficult to predict how the staying power of these car sharing services. Another example is we assumed that public transit users would be more likely to maintain their status as a public transit user than invest in a vehicle. So we use this transition matrix to follow 10,000 people in each of the 4 cities. So for each person, we assigned him to one of the 9 driving categories in one of the 3 states. And these distributions across the populations were specific to each city. So using the transition matrix, we simulated the changes in the population over time using a MATLAB program. So here are the results of the first 2 cities. And you can see the green represents car owners, and red is car sharers, and blue is public transit users. And you can see that there are key differences between the different car sharing models. For example, round-trip car sharing did not really catch on, mainly because it was the most expensive. And the station one car model was the most successful because of its low cost and more flexibility for the user. Here are the results for our next 2 cities. So you can see by looking at these cities they result in pretty much the same proportions across each city, and this is because the transition matrix we used was dependent on the individual qualities rather than the city-specific data. But with more time, we'd love to investigate how the citizens of each city are different from each other. So we rank the cities by population density because our results show that the same proportion of citizens would be interested in car sharing services. So we'd recommend that a car sharing business would look at cities with the most users per unit area. Now Eric will talk about how we changed our model to fit future innovations.
For the future model, we looked at how emerging technologies such as renewable energies and self-driving cars would affect the model. To do this, we first assumed that people will work during their commutes, considering that they're in self-driving cars. This was done considering the fact that time is money and that they'll have newly found time. Furthermore, we considered that future cars will run on a power source of negligible cost. This was done considering the fact that renewable energies are progressing every day and that already solar power is nearly costless over time. With these assumptions, we then use the same model as part 3. However, we did change it by changing the p-scores and the p-values in the sigmoid functions. This was done by adding both the money earned and the money saved in the cars. With this sum, we then subtracted it from the old p-values, which ultimately gave us the new p-values. With these new p-values, we then reran the simulation. As you can see, the simulation significantly changed. The cost efficiency of being a car owner significantly decreased, while the cost efficiency of being a car sharer significantly increased. Specifically, floating one way and station one way significantly increased. Nonetheless, like part 3, all these 4 cities resulted in the same percentage being car sharers. Therefore, we maintain this previous ranking. Now here's Eileen with sensitivity analysis.
We ran sensitivity analysis to the parameters K and C, which were factors in the sigmoid function in the transition matrix. K denotes the influence of popularity on the user, the importance of popularity to the user of the car sharing service. So we see in the graphs here that with an increase of a factor of 5 in K, the graphs have very little change. The graphs were slightly more sensitive to the factor C, which denotes the importance of cost to the user. So we see that the graphs are more sensitive because it makes sense that if price is important to someone, they would be less likely to use something that is less cost effective. So especially for drivers who drive long amounts of time or long distances, owning a car is more cost effective for them than the car sharing service. So the appeal of the car sharing service decreases. But overall, we can see that regardless of this sensitivity, the one-way station model remains the most profitable and most popular of the models. And for that reason, we conclude that our model is relatively robust in that our results do not change. Some of the weaknesses of our model are that we had only a 30 zip code sample size. However, in the end, we found that this sample size was large enough to create a prediction of the entire continental United States. Our matrix probabilities also don't depend on city-specific characteristics. This is something, had we had more time, we would have loved to look more into that, and that would have made our model much more accurate to the cities. We also assume that people could only use one of the given modes of transportation. We understand that people could possibly use multiple modes of transportation, but for simplicity's sake, we assume that we would just take the one that they use more and give them that categorization. We also assume that the total amount of driving done is proportionate to the commute time. This is another thing with more time we would love to look into and expand upon. The strengths of our model are that we were able to consider both rural and urban populations. And because of that stratification, we were able to use all of the United States zip code data within our model on commute time and population. Furthermore, the Markov chain model considers individual preferences and the effects of individual decisions. And within those decisions, we were able to factor in the popularity of a car sharing service. So the more popular it is to share a car, the more common it is, the more likely someone else who doesn't use the service will hear about it and join in. And finally, our model is both flexible in terms of the fact that we can change the values within the transition matrix, and it is robust to the parameters C and K. In conclusion, we categorized the population of the United States based on driving habits, and based on that, we were able to determine the cost of each car-sharing business model. And then, based on that, we were able to create a Markov chain model that analyzed individual decisions. And then we were also able to recalibrate that model based on futuristic ideas of eco-friendly cars and self-driving cars. And in the end, we found that our model is strong, flexible, and robust in terms of K and C, and that one-way station model is the best for procuring the most users in the shortest amount of time, and therefore the most attractive for a business. And we also find that the future is bright for car sharing, as its popularity will increase with the introduction of eco-friendly cars and self-driving cars. We'd like to thank our coach, Mr. McNamara, who couldn't be here with us today. We hope he's doing all right. And we'd like to thank our mentor, Sandeep Silwal, for helping us. And we'd also like to thank Ms. Sangha, our chaperone today, our families, and the Moody's Foundation for having us today and giving us this amazing experience.
Sort of address this a bit. Okay, my first question gets back to those 30 zip codes that you dealt with. You had, there, I don't know, 95,000 US zip codes. What prevented you from just looking up every one of those and plotting them in that scatter plot that we see, rather than just the 30?
Do I push the button?
So the reason we did that was because the website, we used a website that took distances and input and then gave us, used an algorithm to analyze the street distances around that in that zip code. And so each zip code that we used took about 1 to 2 minutes to get that information from and analyze. So it would have been impossible for us to do that within the span of time. And so we only ended up having enough time to do 30 zip codes.
We found the census data for just the time, but we couldn't find the census data for distance. So we had to use the algorithm that Josh talked about to find the distance one.
And maybe you could just even further elaborate a little bit. I know and also you're blocked by the thing. I apologize for that. But could you elaborate just a bit more and discuss like how the 15 rural and 15 urban ones can be considered a stratified random sample?
So we created 2 stratas of rural and urban because they both have distinct characteristics of the time and distance driven. You would assume that an urban area would have a smaller distance, but the time might be greater because it's in a more populated area. So we wanted to break up the zip codes so that we would have an accurate representation of all types of cities and areas in the US. So we broke up to 15 rural and 15 urban, and we used a pseudo-random number generator to find zip codes for rural and zip codes for urban, and then we calculated the time and distance.
Okay. All right. Would you like to?
Yes, one more follow-up on
Yeah.
the same question. So previously you said that there's, 15% of the population is, I don't remember, urban, and 85% are rural, and maybe I have those switched up. But so with respect to that, then is it appropriate to pull 15 rural and 15 urban?
Well, when we calculated the individual blocks for the 9 block model, we used, when we calculated the mean and the standard deviations for that 9, for the distances, we took into account that it's 15% rural and 85% urban.
All right.
Time still? Can you pull up the Markov transition matrix? My question has to do with the first row and the last row, the effects of the assumption 1/3, 1/3, 1/3, and then the 0.4 and the 0.6. Do those matter much?
Yes, they do. But we had to make reasonable assumptions because it's very hard to quantify how probable it is for these people to switch from different states, especially because car sharing is relatively new and we don't know the effect of the business on the population.
That
But
was
with-
something that we would be able, that was something that attributed to the flexibility of our model, because though those are our assumptions, they're easily changeable based on an individual's preferences or a city's specific characteristics if one were to have that information.
And can you give intuition on the K and the coefficient CP in your expression there? Tell me
Yes.
about K and
Audrey, can you pull up the sigmoid function?
So K is the coefficient for S of t, which is the popularity of time step t. So K, the larger K is, the more important the popularity of the program is to the specific person. And the larger C is, the more important the price of the car sharing service is to the specific user. So K and C sort of balance out the preferences of the specific user.
I think.
Great.
Okay,
Thank you
thank
very
you.
much.
Thank you.